Okay, well, we've had a look at SQL and we've seen that it's a pretty powerful language for manipulating data. But it can't do everything. So let's take a look at some of the things it can do, some of the things it can't do. So obviously it can define data, set up constraints, got a very powerful query language, and there's even a little bit of abstraction via views. So that gives you quite a powerful mechanism to define, store, and extract data. But even though it's powerful and nicely declarative, it isn't something you can use to build complete applications. And it's even a little bit deficient in some aspects, such as general constraints, which we'll talk about a little bit later, but we'll see the beginnings of how you can implement better or more powerful constraints. So we need extensibility from the level of SQL. So it'd be nice to make SQL even more powerful than it is as a data manipulation language. But also, clearly, we've got to have some kind of programmability. All right, so how might we go about extending SQL? Well, we could add some new data types. You could add object orientation if you thought that was a useful thing. More powerful constraint checking I already mentioned. If somehow views are kind of fixed a little bit, and you can specify a view like a table, and then you can say where to filter out some aspects of the table or some tuples from the table. But it might be better if you could generate just the tuples you needed. And to do that, you need to be able to feed some data into the view. But views are kind of fixed objects that always run the same. They may give different results because the underlying data's changed, but they always run the same. And also something that's very powerful and which we'll look at is have actions that are triggered by things that happen in the database. So we've already seen some aspects about how update and delete and insert can be affected by various constraints, but we might want to be able to define our own types of actions to make updates and more powerful than they currently are. So all of those things are good and they give us a sort of super SQL, but they still only assist in developing applications. They don't give the ability to define full application. And to do that, we need a programming language, essentially. And that's something that SQL is not. But these are the kind of things we want. Implement user interactions, SQL can't do that. Control sequences of database operations, similarly, it'll take in a select statement and it'll execute it, give you back a set of results. That's about all you can do. And similarly, that's about the extent of user interactions as well. If we get back query results, we often want to process them in a way that's a little bit more sophisticated than what you can do with SQL itself. And of course, ultimately we need to build a web interface so that users can access the data. And SQL is so dumb that it can't even do something like factorial. Someone must have said that at some point in the past because Postgres actually added a factorial operator. All right, so here's an example of the kind of thing that we might want to do. So a bank customer tries to get some funds out of an account. If they don't have enough funds, then we print out insufficient funds. Otherwise, we update the account and print out the new balance. All right, if we wanted to try and do this in plain SQL, here's a possibility. We could try 3 statements. So the first thing we could do, we could check whether the balance is sufficient. And if it's not, then we could return insufficient funds. So in PostgreSQL, that's what would be displayed, insufficient funds. If there were sufficient funds, then of course we'd update the account and we'd reduce the balance by the amount of the withdrawal, and then we'd print the new balance. Now, a couple of things to notice here. Somehow the account number and the amount have made their way into this SQL. How do they do that? Interesting question. It's kind of like there are a bit parameters to this piece of SQL code, but there's not an obvious way to get them in. All right, well, 2 things can happen here. We can display insufficient funds and the update won't have any effect, and we'll display an unchanged balance. The other thing that might happen is that we don't display insufficient funds. That first select doesn't return anything. We then update and we display the changed balance. Right, I've already alluded to some of the problems. SQL doesn't allow us naturally to feed in things like account number and amount. And it always attempts the update, even when we know that we don't need to. And a kind of simple thing, but we need to evaluate that balance check twice. And it always displays the balance even when it's not changed. Maybe that's useful if you've got insufficient funds anyway. But if we want to implement something like what was described here, then we need more. SQL by itself doesn't cut it. So that gets us to the point of thinking, how do we programmatically interact with database? Well, we need a combination of SQL effectively, so it does a very good job of data manipulation, but we also need some sort of conventional programming with control structures, input, output, and so on. So how we achieve this can be realized in a number of ways. We can get all of this if we have an external program that interacts with the database system by perhaps feeding in SQL commands. So the programming language interpreter lives outside the DBMS. It sends SQL queries to the DBMS and it reads back results. We haven't talked about that yet, but we certainly will later in the term when we discuss how you can interact with databases using Python. Another possibility is to embed an SQL library into a programming language, and PostgreSQL has a way of doing that with C. It's quite a low-level library. And the final possibility, which doesn't give us all the power we need, but it certainly allows us to extend the capability of the database, is to use special purpose programming languages that are actually inside the DBMS. So we're going to focus on that one certainly for the next few videos, and we're going to do it via stored procedures. So here's an example of what a stored procedure might actually look like, and this code here will actually solve the withdrawal problem. So what we're defining is a function called withdraw, which takes 2 parameters, the account number and the amount, and it returns some text. All right, it seems to have a local variable called bal. We can extract the balance from the accounts table using the account number. We can check whether the balance fits, or whether the balance is sufficient or is larger than the amount we're trying to draw. If not, then we return the text insufficient funds, and that ends the database's work. It doesn't do anything else. because we've got if then else, and this stuff will only be done if we do have sufficient funds. All right, and then if we have sufficient funds, we update the account by reducing the balance, and then we fetch the new balance. We could have actually computed the new balance without having to fetch it again, but just in case it doesn't work or something, we may as well go back and look at the accounts again after it's been updated. And then we return text, which is new balance concatenated with the actual balance. All right, so if we invoke this function, it would pretty much do what we wanted. We'd have to feed in two values. If we didn't have sufficient funds, it would print out the message. Otherwise, it would make changes to the account and display the result of those changes. Right, well, this is actually code in a real stored procedure language called SQL PSM. So what are stored procedures? Well, basically they're small programs that actually live inside the database, and they can be invoked from SQL queries, or they could be automatically invoked by triggers, or they could be invoked from an external program which calls an SQL query which invokes a function. All right, so the code that we saw on the previous slide is a standard. It kind of sits alongside the SQL standard, but the real problem with SQL PSM is that it wasn't standardized until 1996. But by then, pretty much all the major database vendors had already invented their own stored procedure language. So Oracle had PL SQL, for example. So SQL PSM hasn't caught on. A few DBMSs actually support it, and I think maybe even MySQL does, but Postgres doesn't. However, it does support stored procedures in a whole bunch of different languages. We're not restricted just to Postgres' stored procedure language, PL, PGSQL. But you can write stored procedures in SQL, and you can create functions in SQL that kind of behave a little bit like views, but they can actually take parameters. And so you can feed values into the view. And there's a bunch of other languages that you can write stored procedures in Postgres. And the reason that all of these languages are available is that the definition of stored procedures in Postgres is by just string. So you write a string which can be a Python program, a string which could be an SQL statement, a string that could be a PL/PG/SQL program. And all of those things can be stored in the database and then fetched up when they're invoked, and they can be interpreted appropriately because we know what the language is that's stored in the string. But that's really the trick, the fact that they're stored as strings. A lot of other DBMSs will actually have the stored procedures at a higher level, basically at the same level as SQL, the same lexical level as SQL. So they're kind of like SQL statements, whereas Postgres stored procedures are actually strings stored in the database. And just to make this point, that PL/PG/SQL is actually executed inside the Postgres engine. So you'd load up some PL/PG/SQL code and you'd start executing it. If part of the PL/PG/SQL code is an SQL statement, it will send that off to the SQL execution engine and get back the results to continue with. If it's a control structure like a for loop or whatever, it will use the procedural statement executor, which might eventually invoke the SQL engine and get some results back. But the real point is, all of this is happening inside the engine. This is quite different to what happens when you've got a Python program that's invoking well, it's sending an SQL statement off to the database along a pipeline and then reading back the results along that pipeline. That process is actually quite slow, but not slow enough to not be extremely useful. So having the interpreter embedded in the DBMS makes things very efficient, especially when the procedural code is invoking SQL statements. Alright, so what do Postgres functions look like? Well, we're going to have a whole bunch of videos on PLPG-SQL, but we'll start off with something simpler, functions defined in terms of SQL. However, this gives the overall structure of Postgres function definition. So create or replace should look familiar. It's the same notation you use with views. Then you give the name of the function. And in the case of an SQL function, you just give a list of types. And then you give a return type. So a function returns a value of a particular type. It can actually return a set of values. And the notation you'd use for that is rather than returns single type, returns set of type. The other thing here, we've got the definition, the function body, which you can see we're using these $$ things. And if you remember from the syntax of PostgreSQL's SQL, that's just a string. And finally, we have to tell Postgres what language the function's written. So all Postgres functions are actually going to have this kind of external structure. The difference is going to be in what's in here in the function body and this value here, which tells us how we should interpret what's in the function body. Notice that we haven't got argument names here, we've simply got types. That means that somehow we have to be able to reference these things inside the function body. And in SQL functions, you do that by saying $1, that'll refer to that first argument, $2 refers to the second argument, and so on. And the return value for an SQL function, there's no explicit return like you have in C. It's just the result of the last SQL statement. So you can actually put multiple SQL statements in here if you think that's useful. And in theory, they could be updated and so on as well. All right. And if you want to find out more about how you define SQL functions in Postgres, you can have a look at the Postgres document. All right, so let's jump into an example. So we want to write a function that will return a set of information about bars in a particular suburb. Okay, so create or replace function. The name of the function is hotels in. The argument is a value of type text, which is a suburb name, and what it returns is a set of bars tuples. Okay, bars is a table. We can write the name of a table in this context, and it actually means the type of the tuples in the table, or the schema if you like. So when we write bars here, that actually means the table bars. Where up here, writing bars means the type of the tuples in the table bar. All right, so the definition of the function is a select statement where we select the bars which have the address corresponding to the parameter that's passed in. All right, you can see an example here. So we call get me all the hotels in the rock, and it gives me back that set of bar info. And if we ask for the hotels in Randwick, well, apparently there's only one. I don't think that's true, but for our beer database, that's the case. Okay, so that's one example. Here's another one, which I think may have been one of the exercises on the beer database, to find the name of the cheapest beer at each bar. And when it says cheapest beer, It actually means cheapest beers, because there may be multiple beers that are equally cheap. All right, so how might we do it in plain old SQL? We could create a view, cheapest, and here notice that we're writing things that look like parameters, but these are actually return attribute names. So these are the names of the values. These are names that we can use to access the values in the tuples that are returned. All right, so we do select bar, minimum price at bar, using a group by bar. So this is going to give us a table of bars and prices, where the price is the minimum price that beer is sold at that bar. All right, so we've got a view that can give us that. How do we use it to actually solve the problem? Name of the cheapest beer at each bar. All right, well, we use the cells function again, because the cells function tells us beer, bar, and price. So we want to get the name of the beer, and we want the beer whose price, I guess this possibly could have, rather than being s dot star, it just could have been beer. So we just get the name of the beer. But here we're actually going to get the name of the beer, the bar where it's sold, and the price. All right, so we want a beer from this bar where the price of that beer is equal to the cheapest price that any beer is sold at that bar. Okay, notice that here we've got a correlated subquery. So this this S tuple carries down to here, and this is the bar name for the current S tuple. And we're also interested in where the price stored in that tuple is equal to the cheapest price at the bar for that tuple. Okay, so we've seen examples of things like this, so hopefully that's nothing surprising there. Here's an alternative approach, and you know, like programming languages, there are lots of ways you can solve in SQL. Okay, so here we're going to define a function, lowest price at, and feed in the name of the bar. And we're going to be looking for the lowest price at that bar. And how to do that? It's pretty straightforward. We just select the minimum price from the bar. How do we know which bar we're talking about? In this case, it's actually passed in as a parameter. And what we return is the price itself. So we return a floating point value which we derive from that aggregate. All right, so we've got a function that will give us the lowest price for a beer at that bar. And this makes the final query a little bit simpler. So we're looking at the cells table, and we're looking at the price for each tuple there, and for each tuple we're checking whether the price for that particular beer is equal to the lowest price at the bar. So price and bar both come from the cells tuple. And what we eventually return are any tuples that satisfy this property here. So defining without a function, defining with a function, you can argue about which is simpler, but it was to demonstrate the point. All right, another thing, functions, when you write functions like that, they kind of look a little bit like views. A view, you give an SQL query and it gives you back a set of results. Okay. In this previous example, this was actually giving us back a single result, but I think the earlier function gave us back a set of tuples. Okay, so it's giving us back a table, kind of like a view does. So here's an example of getting a list of, you could argue, more readable information from a set of employees. So we put in the given and family names together, separated by a space, and we're putting the street and town attributes together in a string, and that's going to be the address. Right, so this is how we define it. Hopefully I've made clear that that double pipe symbol is string concatenation. So given is a string, that's a string consisting of a single space, and that's another string, and we concatenate them all together. All right, and we use that simply by invoking the name of the view, treating it to some extent like a table. All right, this is how we do it using an SQL function. Now, it turns out to be a little bit more complicated here, because we're not actually just using the employees type. We're using a new type, which is a sort of subset of the type of the employees record. So in order for this to work, we actually have to create a new type. And this, we've seen examples of this when we looked at create type. We're creating a new tuple type. The tuple type has two attributes. Both are of type text. The first one is called name and the second one's called address. Okay, so this is how we define the function. Notice that it doesn't take any parameters. Returns a set of emp records. That's how it does it. Same query as we had before, and that's how we'd use it. You might say, yeah, that's a little bit more complex than defining the view. That's true, but we're not actually exploiting the fact that we could potentially give this function parameters, and then we could actually use those parameters there. Okay, in any case, so to some extent, functions without parameters look a little bit like views. All right, so that's a little introduction to stored procedures. Why do we need them? Because SQL by itself doesn't quite give us enough. It's certainly powerful enough to answer lots of questions about data, but to write an entire application, we need a little bit more computational power. And this, and certainly PLPG-SQL is a first look at doing that. None of this stuff still gives us the kind of programmability where we can write user interaction, or we can write a web interface, but it's a start.